So we've been talking a lot about the hydronium ion as a way of tracking acidity and basicity. We could do the same with hydroxide ions as well. We have a way of measuring both of these. We tend to do hydronium ions that gives us pH, but you'll also see pOH, which would be corresponding to the or would correspond to the concentration of hydroxide ions instead. And so we can easily convert in between the two if we know one, right? Because we have this equilibrium expression, and this will our give it a second and everything will come to equilibrium. And so if we know the pH or we know the hydronium ion concentration, we can use this equilibrium expression to find the hydroxide ion concentration. Remember, Kw is always going to be equal to 1 times 10 to the negative 14th. And so just dividing that value by the hydronium ion concentration gets you to the hydroxide ion concentration. This Kw value, it's an equilibrium constant. It's also called the ion product of water. I don't know, I just call it Kw. You might also see it written in some textbooks omitting the hydronium ion and using the proton expression instead. And when you do it, it's the exact same thing. Remember, the H plus ion concentration we can see is exactly the same as H3O plus. And so that pH, right, that we've been talking about, that pH, the P is telling you negative log, and the H is telling you H plus. So if we were going to track things in terms of hydroxide ion, we would be looking at pOH if we were looking at OH minus. And so let's look at that. Let's look at, this other way of expressing acidity and basicity of a solution, which is going to be our pOH. So our pOH is going to be equal to the negative log of that hydroxide ion concentration. So for just pure neutral water, right, it's going to be 10 to the negative 7th, just like our hydronium ion. They have the same concentration when there's no other acids or bases around. And so that would be a negative log of 10 to the negative 7th, which will give us a value of 7. So that makes that neutral range for both the pH scale and the pOH scale the same. What changes about it is that with pOH, right, it's going to have a high concentration of hydroxide ions when it's basic. And so that means on the pOH scale, small numbers are going to show basic solutions rather than large numbers. And so we've got basic here on this end. And you can see on the pOH scale, we've got 0. And on the pH scale, we have 14. Looking at our acid side of this scale, when we're looking at the pH scale, we have a low value for our acid, and when we look at the pOH scale, then we have a very high value, like 14. And so looking at pOH just kind of flips our scale in a sense. And it's really tracking low numbers on the scale are going to correspond to what you have a high concentration of. If you're looking at pOH and you have a high hydroxide ion concentration, you have a lot of base around, so you're going to see a small number. But from this and from that Kw expression, we can actually pull out this really handy expression that the numeric value of our pH plus our pOH will equal 14. And so that's like what mathematically what we're doing to get here, right, is we're taking that Kw expression. So Kw, remember, is equal to 1 times 10 to the negative 14th times these concentrations of hydronium ion and hydroxide. And I'm just taking the negative log of the whole thing. And so that 14, that's really equal to the negative log of 1 times 10 to the negative 14. And pH is going to be the negative log of H3O plus. And my pOH is the negative log of hydroxide ion. So I'd like you to be able to work in either pH or pOH. And it's important to be able to use this ability to convert between them. However, for the most part, out in the real world and in just the lab environment, pH is going to be the standard that we track. It's more common. At this point, I'd also like to talk about a little algebraic thing as well. If you know the hydroxide ion concentration and you want to, you want to know the hydroxide ion concentration and you know the pOH, Or the other way around, you know you want to know the hydronium ion concentration, you know pH. Remember that the algebraic opposite of a log is base 10. And so I want to briefly show how we go from an expression like pOH is equal to negative log of hydroxide ion to hydroxide ion is 10 to the negative pOH, right? So these are just two ways of solving this problem. So if I want to do like kind of the algebraic opposite and isolate hydroxide ion, what I really need to do is first get my negative onto the other side. So I'm going to divide everything or multiply it either way by -1. And so I'm going to have negative pOH is equal to the log of my hydroxide ion concentration. And then I'm going to take both sides of my equation and do them to the base 10 to the exponent. So it's like 10 to the negative pOH and 10 to the log of the hydroxide ion. In this case, that 10 to the n log cancel each other out. And so then I get hydroxide ion is equal to 10 to the negative pOH. So I'd like you to be able to be comfortable going back and forth between those two. Let's do an example. So what's the pOH of a solution with an equilibrium concentration of hydroxide, or sorry, hydronium ion that is 9.5 times 10 to the negative 12? There are actually a couple ways of solving this. I'm going to show you two different ways. So here's method one. Method one is going to use KW. KW is going to be equal to that concentration of hydroxide ion times hydronium ion. So 1 times 10 to the negative 14th is going to be equal to the hydroxide ion times my 9.5 times 10 to the negative 12th molar. I'm going to solve for my hydroxide ion concentration. I get a value that's 1.001053. And so to calculate the pOH, I'm just going to take the negative log of that. So my pOH will be equal to the negative log of that 0.001053, which will give me a value that is 2.98. All right, that's one way to do it. So let's look at another way. So I have this hydronium ion concentration. I'm just going to take the pH. So the pH of this is going to be equal to the negative log of that concentration of 9.5 times 10 to the negative 12th. So that pH will be equal to 11.022. We'll do 0.02. All right, so that's my pH value. I know that 14 is equal to pH plus pOH. So I'll just plug in that pH value here. So 14 is equal to 11.02 plus pOH. That means if I subtract that 11.2 from both sides, I get 2.98.